Okay, so from today we'll start to talk about recommendation system. So this is a new topic. So we'll talk about the theory underneath of that and how we approach it. And you are going to so you're going to do some problem related to this explicitly and to practice those techniques and skill sets. Okay, so so recommendation system is everywhere. So basically, you can think about Netflix and recommend movies, Amazon recommend and stuff, and if you have some Google's, it recommend like advertisements. So like recommender system are actually the system to recommend items. It's very useful. So the information they have is the user based on the various information they already have. For example, their past viewing history, their purchasing behavior. And for example, Netflix, they will check your previous histories of viewing the movies. For purchasing behavior, it's like if in Amazon.com, your annual purchasing histories for this. And for example, these are all like important behaviors that can be used to actually and it can be used to help us to build a good recommendation system. For example, which movies they rated high or low, which ads they click on or not, as well as some side information such that as a demographic of the users, information about the content of the items, such as title, price, and genre. So this is very, very important because and later on in your project, the homeworks, that you are going to see such kind of things. Not only you have the information of those and users interact with the items, but also sometimes you have some side informations. For example, those movies, you can get some information from movies titles and so on. Okay, so for this lecture and probably next lecture, we'll focus on a very important class of the recommendation system. It's called explicit feedback. So what we do is we give an explicit feedback to a system in terms of rating. For example, it gives the scores from 1 to 5. So this is very common in the Netflix. For example, you watch a movie. After you watch the movie, you give the scores from 1 star, 2 star until 5 stars. So this is very common. So basically, this AUI is just take 5 values from 1 to 5. It's actually the rating that user U gives to the movie I. In total, this matrix have n number of users and n number of the movies. So basically, the number of views and we'll have an m of users and the number of the movies that will be n. Usually, this matrix will be very large. A good way of thinking about is, the number of users of the Netflix could be like 100 millions of like, and and it's very very, very powerful. So in Netflix, the M could be like 100 millions or something like that. N is the number of movies. That's like, still a lot. It could be like 10 millions of like 5 million movies. But like this matrix will be very large, but the key things is this will be very sparse because most of users don't watch all the movies, right? So because they don't provide any feedbacks on most of movies. They only provide feedbacks on very limited movies. For example, if I watch a movie, I maybe like watched like 100 movies. Until now, I can only give the ratings for those 100 movies, right? So for other majority, 99.999% of movies, I actually haven't watched it. So I cannot give the ratings or feedbacks to those movies that I didn't watch. So we assume the data is missing at random because the user hasn't interacted with that movie. So basically, if they haven't interacted, the data entry will be 0. Many years ago, so this is a very famous problem. It's called Netflix price. So this is basically, I think it's 2006. They released a very large data set, right? So this is about, let's see, I think it's a wait, 100, like 100 million. I mean, 10 to the 10 to the 8th movies ratings, 100 millions and movie ratings. From the number of users, the user that we have is almost like it's like half and half million, something like that. 500,000 users. The movie we have is almost 20,000. So with that large size of training set, but we have almost like 100 millions movie ratings coming from 500,000 users and 20,000 of movies. 99% of this rating matrix will be sparse because the most entries are missing data. The only actually has the entries that has entries is only takes only 1% of the entries that we have. So you can look at this, something like this. So these are the users, right? So these are different users. These are movie 1 to movie 11. So this is very much oversimplified version of what we're doing here, right? So, and you can see for this user, it actually rate movie 1 as 1 star, movie 4 as a 5 star, and so on, right? So for this, we only have 11 movies and we only have 7 users, okay? The key is, based on this information, can you predict for this third users what this rating will be, right? So we know this user hasn't interacted with these movies. So this is a question mark here. Can you come up with an algorithm actually to predict this question mark here? Okay, so this is basically the fundamental questions on recommendation systems. So this is, and this type of problem is called explicit feedback. So basically, the user and the item or the movie, the user actually watched the movie, and also they provide explicit ratings on these movies, right? So for example, 1 star to 5 star. If the user have watched a movie but didn't give any ratings, for example, you watched some movie but you didn't give any ratings, I do not consider this data entry is valid. So just this still considered as a missing entry. Okay? So this is fundamentally different. So that's why we call it explicit feedback. So that means the user actually provide very explicit feedback to this movie. All right, so most of the time, we are trying to solve this problem by using matrix factorization approach. So you can think about this whole process is being done through, say, we have a D different topics for each user and movies. Okay, so that means we are thinking about trying to categorize all these movies, right? 20,000 movies. into 3 different categories: action, romance, or drama. So this is just like we made it up. Just think about this. So maybe for the movie I, with the topics of HI, we have 0.2 with action, 0.01 as the romance, and 0.5 as drama, which basically means it's more like half drama. I'm a little bit action, but definitely no romance. For next, you can describe a user U with a topic. So basically, how much he or she likes the action, romance, and drama. For example, 2.5, 0, and 0.8. For that particular user, he or she likes the actions, and the drama definitely has no interest in romance. So what it is and what is the rating going on says, I'm going to interact these movies with the users. So the way that we take this interaction is I'm going to take the inner product, basically multiply them together, then sum of that. Okay, so if we multiply these 2 vectors and the sum of the entries, we got 0.9. So that means if that person, right, with that user, you just happen to watch the movie I, this is the rating that user will provide, which is 0.9 right here. All right. So the issue is, how do I know this topics has that kind of vector? And how do I know he or she has that kind of preference, right? So how do I know that? So the way we do is we trying to factorize that matrix of A into the matrix of W and the matrix of H altogether, automatically. Okay, fundamentally and speaking is I want somehow this vector multiply this vector, and in the product of these 2 vectors to be as close as 1 as possible. Same here, if this second vector versus second vector of W here, if we take the inner product of these 2 vectors, we want this value to be as close as 2 as possible, and so on. Okay, and of course, sometimes you will see those values are actually negative. If we have a negative values, it might be difficult to interpret, right? So if the value is positive, you can interpret how much I like for those categories, or like how much it is for those categories. Whether it's action, romance, or drama. So this just give you some like idea what are we trying to do here. So basically, for those entry that is colored with yellow, so these are the training data. We already know the values. And we want to ensure the corresponding 2 vectors. If we take the inner product, we want this value to be as much close to and to this like entries in this matrices. Say if we have that kind of the inner product and a product, and we have these 2 matrix W, and we have the matrix of H. So then we are ready to answer the questions, and what is the value on this question mark. Right, so the way we do is same thing, that we just take the inner product with this vector and that vector. So this will be my and my predictions. If this user watched that movies, that would be the rating I will predict. So it's very simple, just simple matrix multiplications. Of course, when we make the predictions, our trainings, we don't know the topics of user and the movies. We don't know what exactly these 3 values and represented to. Right? So and it could be represented to any kind of things. but we're trying to interpret this as a type of the movies. But of course, this is just by one way to interpret. But of course, if we have a negative values, it will be very hard to interpret. Okay, so this is another way of thinking, right? So we have all these movies right here, and we have a comedy, we have an action, we have a horror movie, we have a romance. So they are in the four different angles that the movie could be. And for example, for this Die Hard is more like actions. For example, Saw is more like horror movies. Titanic, it will be romance like movies, and and Idiots, it's more like comedy movies. So basically, each movie we are going to trying to make sure and trying to make the movies into their categories. And also, like different users, they have a different preference. For example, these users might like both the romance and horror movies, right? So, and also this user just like to watch the comedies, for examples. And this users liked actions and the horror movie at the same time, and so on. Right? So different users has different preferences. So basically, they will overlap with those and the movies in a such way that if you want to recommend that particular users with the new movies, for example, if this girl hasn't watched the Twilight, these two things overlap because they like romance and the horror movies, and in the same time, say that Twilight is also romance and horror movies, then the Netflix says, I'm going to recommend the Twilight movies to that girls. Right? So this is a very common way of thinking. But on the other hand, we know the Man in the Black right here is a comedy and action movies. So I would not recommend Man in Black to that girl because she will not be interested in. Right? So this is basically the philosophy or the idea underneath of this and recommendation systems. Okay. So let's just talk about and the method and the theory underneath of this. All right, so let me just talk about something here. So let's see. Maybe like this. Okay, so that's good. Let's see. Okay, that's clear. Okay, so all right, so we have a talk about this problem. Basically, this is setup. So we know what we know, given. Oh, given I have a matrix, which is A. We know it's M by N. And so M is the number of users. N is the number of the movies or items. And particularly for AUI, so the row is the users, the column is an item. Is the ratings from 1 to 5. Okay. Which is good. So the key is I'm expecting this AUI expect AUI is approximate FW and inner product of H of I transpose. So both are actually a vector. So you can think about this as being a row and HI transpose. HI is a row, HI transpose become a column. Okay. So you can take the inner product directly. All right. So how to approach it? So basically, I'm in vector form. This A is approximately, you can think about W times H transpose. Okay, so this is matrix factorization problem. Trying to factorize this matrix A into the product of two matrices, W and H. So in more precise way, it will be W and the dot H transpose. Okay, so method one. So you're going to implement that in your homework project. Direct low rank solutions. So and basically, and what does that actually means? So you are going to propose the following optimization problem, and almost every time that you have seen the so we have one hidden and assumptions is A is low rank. Okay, so this is one of very much an assumptions that we have, and we only have a missing, and we have a missing data. That means 99% of entries of A is missing. We only have like 1% of entry being not missing. So basically, A is a rating matrix, and we also need some like and other like terminology. For example, omega is UNI, AUI is observed. Okay, so basically these entries UI, that AUI is observed. So this only takes about only 1% of entries, right? So these are the data we have. So we're going to propose the following an optimization problem. To solve this like low rank solutions. So the loss that we have is the following. Different color. AUI subtract WU HI transpose square. Okay, so I mean, this is basically the mean square error plus lambda of the Frobenius norm of W square plus H, the Frobenius norm of H square. Okay, so, and what is argument that we're trying to minimize? Is we're trying to minimize the W is M multiplied by K, and H is in M multiplied by K. Okay, so, and I want to remind you, we're trying to find out such kind of W and H, and W and H are low rank. So what does that mean is my K is actually, you can think about the rank, that K, okay, is significantly smaller than the minimum of M and N. Okay, so that such that it can, I mean, sure, this is low rank. So, all right, so let me just add one more color here. So, okay, so right here, this term right here is actually a regularization terms. This happens a lot in all sorts of machine learning and deep learning, practical machine learning. So these kind of regularization term is to avoid overfitting. We have talked about overfittings again and again and again. So this is very important. If you don't put this, it's likely you will have overfitting issues. And of course, how to find out this lambda here, you can using cross validations to find out the best lambda for you. Okay, so you can and perform all sorts of cross validations. Or sometimes you just set lambda equal to 0.1, and hopefully you can get a good result. Okay, so these are like and different approaches. And also, in practice, we're also going to add some baselines. For example, this is also very important in some problem as well, just because and you can see some, and sometimes you are getting like negative values or something like that. It doesn't make much sense. I will talk about this specifically, probably in the next lecture. But like more natural way to do it, you can do, and you can put those kind of user specific and item specific baselines. So that means you could add user item baseline. So what is that? This is AUI is actually equal to, so these are universal baseline mu as B of U, which is the baselines for the user, and the C of I, which is the baseline of the item. Then I plus W U, then HI transpose. Okay, so these are the important part. All right, so, and also K right here, as I said, you can think about as a rank of the matrix that we'll be interested in. So you can think about this way as a, and RK is the latent feature spaces. So you can think about if we previously you think about action, romance, and I believe it's action, romance, and drama, right? So we consider if that's the cases. Example, if we think about action, romance, drama, so that means make k is actually equal to 3. Right? So we consider 3 topics of the movies. All right. A little bit more things, and we already mentioned about the WU and HI. U youth user, which is you can think about. I'm going to call it like youth row of W, which is W U. Then the ith movie, like ith item is the ith row of H, so it's HI. All right. So the inner product of these two, you can consider as a measures the interactions between ith users and the youth movies. So basically, this actually measures the interactions. I'm going to write here. So this measures the interactions. All right. So these are the setup. In fact, I already talked about. So many of the parties actually commonly ask questions in the during interviews. All right, so these are like a bunch of points here. So so there are multiple ways that we can do it, right? So this is setup, but there are multiple ways to solve it. For example, if case 1, if we have no regularizations and my A is fully observed, no regularizations, plus this A is fully observed. Okay, so that means what we have is the following. So this optimization becomes the minimum of W in the M times the K, H in R N times the K. Okay, so we have a summation of U of I. So that means we have 4 observations. So that means this becomes A U I minus of W and HI inner product squared. And of course, we can turn this into vector form since we observe each entry here. this becomes same minimization problem, but we can vectorize in terms of matrix. This is actually a Frobenius error. Square of the Frobenius error. Okay. If that's the case, it turns out we have a solutions. We have analytical solutions. But we need to assume this is fully observed and no regularizations. Okay. Again, commonly asked questions during interviews. For this, we have a solutions. The solution is very simple. I'm not going to go through the math very much details. It should be taught in the machine learning courses. It's just do the singular value decompositions. On a SVD. Okay. And keep top K singular values. Okay, so this is very important. So that means what I'm going to do here is I'm going to turn this A into U sigma B transpose. Okay. So what is W here? Okay, W here. I'm going to so I'm going to take the top K singular value. I'm going to take and approximate this with a top K singular value. So this is like 1 to the kth columns, sigma 1 to the k, and the V is 1 to the kth column, but take a transpose. So yeah, so that's what you are going to get. So what you can get is and you can propose your W's becomes U and the square root of sigma 1 to the k, and your H and your H transpose becomes square root of sigma 1 to the k V 1 to the k transpose. So that implies the H is V 1 to the k square root of sigma to the k. Okay, because this is diagonal, you can take transpose or whatever things, it doesn't matter. Just everything, the operations is on the diagonal part. So from singular value decomposition, you know the exact solutions were like this. All right. But there's no closed solutions if you only have for partially observed data. So that means if you only have partially observed cases, you cannot solve it like that, right? So this is not, and this won't work. So you need to do something different. Okay, so the next, we are going to talk about the method actually will work. So this is the case one. The second case is the case two. Is the first time that I'm going to solve it. For this case two, I also want to demonstrate the code. I want to say this is a very important part to show what is the code look like. In the next couple algorithms, you have to implement by yourself, right? For example, the algorithm that I'm going to mention momentarily. Okay, so algorithm. So this is case two is you have partial observe and regularizations. So the method is a very commonly used method. If you remember the lasso, that's the similar and method you're going to work with. It's called ALS, alternating least square. Okay, so the objective, to be more precise, is the following. I'm going to using f. This is the function that we're trying to minimize, right? So this is a variable of W and H. W and H are both matrices. Okay, so they are like skinny rectangular matrices. AUI minus WU HI transpose square plus the regularizations. The reason I put half is just because it's easier when we take differentiations, it can get rid of the coefficients. Right, so this is the regularization and also has a partially observed cases. So this shows this is partially observed. We don't have the full observations here. Okay, so the algorithm is very straightforward. Is the algorithm what I'm going to do is called iteratively fix either H or W, then optimize the other. So what does that mean? That means if I fix W, then optimize for H, or fix H, optimize for W. Okay, so and the pseudocode is the following. So the input is partially observed A, and you give some initial values for W and H. For T equal to 1, 2, fix W and update H. So that means this is the first step. I'm going to treat W as a constant. Then I'm going to minimize my objective functions with respect to H. So I'm going to update my H with respect to this. Here we treat my W as a constant. Same thing, I'm going to move forward by fixing the H and update W. Okay, so W is basically arguing of FWH. Okay. And also we define, we can do, I'm going to define some of the rows here. Define my omega I is U UI in omega. So that means my I is fixed. So that means these are the entries that my user have watched this particular items or the movies. All right, so now the key is actually we're trying, and we need to solve these two sub-problems right here. So this is the problem that we're trying to solve. Here is that I'm going to do. I'm going to just solve one of that. The other one is going to be solved naturally, similarly. So the sub-problem is okay. So the sub-problem is argue mean of H of 1/2 summation U of I in omega and A U I WH transpose UI square plus 1/2 lambda H. The Frobenius norm square, because here we assume my W is fixed. So the other, and then the other regularization is just being treated as a constant. Okay, so this is basically the term, right? So this is the sub-problems that will assume my W is a fixed. So this actually can be separated as following. I'm going to switch the order of the minimizations and the summations, and I'm going to reorder the summations a little bit. All right, so this is equal to I from 1 to the n. So basically, I'm going to loop through all the items from 1 to the n. Then argue mean of hi of 1/2 summation. I believe it's going to sum with respect to u in these cases, but I'm going to say it's u in the omega I, right? Because this is already, I define my omega I right here is the u's, right? In this case, I is a fixed. Okay. So because I already pull out my summation of I from 1 to the n here, this is becomes AUI minus WU H of I transpose square plus 1/λ/2 of HI to norm. So basically I separate each row of H. So think about this H as being like that. So your H is like this, right? So this is your H. And one specific row here, so this is ith row of H, right? So you call it HI. All right, so we are trying to minimize row by row for this H matrices. So we have from H1 to Hn, right? So we separate things from 1 to the n. So we have n rich problems need to solve. So basically, we separate this complicated matrix optimization problems becomes n different separate ridge regression problems, right? So and each of this is being separated out. And each of that has a k different variables because this ui, sorry, the hi is a vector of rk. So, and with each with k variables. So this is, I mean, a very good thing because this actually can parallel easily. So this is very good because it can and easily implement in GPUs. This n ridge regressions are independent with each other, right? So if these problems are independent with each other, it's easy to be implemented in different cores of this, computing units. So it's very easy to parallel. So you can calculate all this H1, H2, H3 to Hn independently. Okay. So that means we only need to solve for one H1 or Hi, that will be enough. Okay, so let's do it. So how we do it? So we do it here. So we're going to taking derivative with respect to Hi. Okay, so so this will be partial Hi 1/2 summation ui, sorry, the u in the omega I just copy what you have. All right, so you just take partial derivative with respect to hi. Okay, so let's do it. So, I mean, this is a quadratic functions. This is actually a two norm, right? And this is also like a row in the product of a column, right? So this is actually this. If you still remember the optimization that you learned, this is minus summation u omega I, then AUI minus WU HI transpose. So basically copy what you have, multiply WU. Okay, plus the lambda HI. Right, so you want this to be 0. Okay. Of course, it will be slightly easier if we switch the order here. Right. So I mean, this is basically the same thing. Just one row, one row, one column. You just multiply and the dot product and together, right? So, and you can switch the order easily. So this is equivalent by taking this HI and then WU transpose. Okay, there's no differences here. All right, so if we take this one, we can solve this whole thing, right? So, it's basically, and we can solve this whole thing. And in the meantime, it will be easier. In fact, we can take everything in terms of matrix form or vector form. So this is something that you should learn in, I mean, previous courses you already did. So this becomes, if we take this into vector form, all right, so we have this WU transpose WU, and we have H of I and H of I. So, and you can always like factor that out. And this becomes the, I mean, and before you do it, you can think about it this way. So minus summation U AUI WU, right? So, so I'm going to and multiply minus 1 on the both hand side. This becomes H of I WU transpose WU plus lambda H of I. Right, so this is basically what you would get and trying to solve. But of course, in the matrix form, so how to turn this into matrix form? So this becomes, I mean, so you can think about this as being a matrix multiplications. But this is it's A transpose of the ith row and then multiply the matrix of W. This is the first part. This is equal to H I W transpose W. So this is actually vectorized with respect to U here. So, but we still trying to solve of HI here. All right. Plus, still need to take this. This is H I lambda. So you can put the identity here just in case if you want to make a matrix. Okay, so here it can be separated out equal to HI equal to W transpose W plus lambda of I. Okay, so these things that you can do it because I switched order here. You have a WU transpose and a WU, then you vectorize it and you multiply them together, becomes W transpose W in these cases. Okay. This is only because I switched order, and this is allowed in these cases. All right. So that's the derivative equal to 0. We can solve for this. So this is basic says my HI star, which is the optimal value to make sure my derivative vanishes. This is equal to, all right, AT, A transpose W, and then you take and multiply the inverse on the both hand side of this thing. All right. So this is basically the solutions of HI star, which is the optimal solutions. And most importantly, you can further vectorize it because the whole I is only the rows of A transposes. So this is further vectorized. So this becomes H star. It becomes A transpose W, W transpose W plus lambda multiply the I, the inverse. Okay. So you can do the same thing similarly for W. So you can get the W star. It's basically the same thing. You can do and derive this. It's very, very similar. This becomes A of H, then H transpose H plus lambda identity of inverse. Okay, so that means this right here solve the first subproblems. Solves the one. So this thing right here solves the two. All right, so this is something that you should keep in mind. And we already ended and the most important thing right here, this algorithm, not only you have can be implemented, and each part can be solved analytically. So these can be solved analytically. You have analytical expressions. All right, so this is the key. And of course, here what we did is we just trying to using this ALS, which is and I think about it as a gradient and basis method, but fortunately we can have the analytical solutions. But we have a multiple methods. For example, we can do stochastic gradient descent. Even with that kind of problem that we want to solve this analytically, these two things could be expensive to solve. Right? So this could be very expensive. Because you think about how large of this matrix that we have. And I want to remind you, the user that we have, and it could be big. So I mean this whole process, and this and inverse of this matrix could be very hard to expand and calculate. So we might think about it different ways. So that we can take advantage of something called stochastic gradient descent. So I'm going to an algorithm 2. I think this is case and algorithm 1 and algorithm 1. Okay. Then here I'm going to have algorithm 2. Algorithm 2 is stochastic gradient descent. If you have very large data, it's very natural that you want to apply the stochastic gradient descent. So because you want to take advantage of very important things is the sparsity, right? And here in these two equation, we didn't take the sparsity at all. We didn't take the consideration of the sparsity. The sparsity is the key that to process this factorization problems efficiently. Okay, so here is the notation right here. And say and I'm using different color here. NUW is number of non-zeros in the youth row of A. We know the most of row. I mean, if you pick a random row of A, most of part is 0, right? Majority part. UIH number of non-zero in ith column of A. Okay, so basically, same thing. You pick the ith columns of this rating matrix. I mean, if you pick random column I, most of part is just 0. And what actually you care is those non-zero entries. Again, you're going to decompose these problems into into various different components. Okay, so here is what I'm going to do. So my objective function here is equal to 1/2 summation. Same thing, right? I want to remind you that okay. So I'm going to take derivative with respect to okay, I'm going to make some changes here. So I'm going to put this summation out. So I'm going to make this to be like this. I'm going to put the half 1/2 here, 1/2 W of U, H of I. Okay, so this is basically the same thing. I'm going to take gradient of each component. Okay, I'm going to take each component of that, because here I'm thinking about the summation of each component, right? So here I'm going to think about this right here is I'm going to denote as FUI and WH. Okay, so this is the summation of each component. So if you can turn this into like that, then you can take advantage of the gradient and stochastic gradient descent, right? But first we need to calculate the gradient for each component, right? So U, FUI, WH is equal to WU, HI transpose minus AUI, HI plus lambda WU gradient H of I WH transpose minus AUI plus lambda HI. And so this is a simple derivative here. So the algorithm is very simple. Okay, so again, its input is the same thing. Input is A, you have initial value of W and H. So it's the same. So input, okay, input is the same. Same as before, as above. Okay. For T is equal to 1, 2, what you do is you randomly pick pick the U and I in this partially observed data set. Right, so this is only partially observed. So this only account less than 1% of entries. Then you're going to update the WU and the HI correspondingly. So that means your WU is going to update it as 1 minus eta t times lambda. So eta t is the learning rate. WU and eta t, WU, HIT, subtract AUI, HI. Same thing, you do the same thing for H. So this is basically the idea that you pick U of I, so this is one data. They're going to using this one data values to update the corresponding rows of W and the corresponding rows of H. Same idea. All right, so this is same idea of a stochastic gradient descent in the machine learning, in other machine learning problems. So this is basically is naturally built in. All right. So basically, this complexity-wise, right? So you only for each iterations, you only need to calculate this inner product once, right? So this is in each iterations, the order of complexity right here is order of k, right? But if you have a whole data set, if you want to parse this data one by one, then in total, this is order of number of omega times of k for one pass of all entries. Okay. It's very straightforward. In fact, you can use this whole idea to parallelize, but it will be more complicated to do so. All right. So, but that's an kind of another topics that we can pursue on. All right. So right now, today we have talked about. Start to introduce this kind of new problem, which is the explicit explicit problem in the recommendation systems. We talk about this and turn this into the optimization problem. So in terms of this optimization problems, we talk about different cases, which is first the trivial cases that can be solved by SVD. Then the general cases that we have partially observed data and with regularizations. Then we introduce two different methods. The first method is alternating least square. The second thing is the stochastic gradient descent. So the reason that we're using stochastic gradient and gradient descent is because sometimes the least as alternating least square will be expensive and it couldn't utilize the power of the stochasticities. So we can further introduce further speed up by introducing such kind of stochastic gradient descent methods. All right, in the next lecture, we will continue this recommender systems. We're going to talk about something slightly more. For example, we're going to talk about non-active matrix factorization, which is the one that you're going to work with in your homeowner project. And also, we're going to talk about some factorization machines. This could be a guidelines and help you for you to kind of to introduce some new methods, something that we already know, to be cooperated into this recommendation system. So in next lectures, two things are the major topics. One is the in the next lecture is non-active matrix factorization. Okay, so we can derive all the things that we have. And also the second one is factorization machines. Okay, so these are the important part. And then we're going to demonstrate demo of ALS. Okay? So these are three parts that we're going to talk about in the next lecture. All right, so that's all for today for now.